Okay, yeah. So thanks again to Dr. Sundari for this opportunity. Um, Now, this is my first visit to CMI and the first time when I have been asked to give a lecture series. So this is also a new learning experience for me. So I guess I will have to learn together in this process. That's the hope of me. Um, yeah. Okay. All right. So the plan, as Sundari mentioned, is to give some a brief introduction into some of the basic definitions, some of the basic techniques that we
देखिए अपन इतनी
in geometric measure theory. Are you asking something? All right. Yeah. And so it's a the field itself is so vast. So I mean, of course, within 5 lectures, there's no way I can cover the entire span and depth of the field. So okay. So what I wish to do instead is that we will, I mean, ultimately, see, at the end of these 5 lectures, you're going to listen to Malavika Pramanik, I mean, another wonderful, wonderful speaker. So, so I plan to sort of prepare you for, like for those lectures, which is my, ultimate goal. Okay. So we'll only follow a particular path, in the upcoming lectures. We'll ultimately try to understand what are the problems related to something called the distance sets. So um, that's what I plan to do. To talk about the field, I mean, vaguely speaking, we study uh, fractal sets. Okay. Now, what are fractals? The word itself, I think, was coined by Benoit Mandelbrot, a pioneering figure in the field. Um, and it was coined from this Greek word called fractus, which means broken. Yeah. So these sets are so broken, so irregular to be studied by classical geometry. Yeah. Which is why you need to come up with new, innovative, novel techniques to understand them. Now, I'm not going to give you a proper definition for fractals. That's because there is no um, you know um, hard and fast rule definition that can span the entire class of interests, like sets of interest. Rather, I'll just give you maybe one or two examples first to at least show some sort of shared features that this class of sets have. Okay. So we will start with something I guess you are very familiar with, the middle third Cantor set. Okay. Is this visible for those who are attending online? Um, I don't. Should I write? Yeah. All right. So let's recall the construction of this set. Right. We start with E0, which is nothing but the unit line segment from 0 to 1. Now E1 is constructed from E0 by dividing this line segment into 3 equal parts. And I'm going to, so that's 0 to 1 by 3, 2 by 3, and 1. And I'm going to remove this open subset or this open interval, right? So that gives me a union of two subintervals of length 1 by 3 each, and that's E1. E2 then is constructed in a similar fashion. We will divide each of these intervals um, into 3 equal parts, and then we will remove the middle third from each interval. This way, ek, or say ek plus 1, is obtained by removing the middle third in ek. And finally, I'm going to define E to be the intersection of all these EKs. Yeah. Now, I guess all of you have seen this set before, right? Um, is this non-empty? Why is it non-empty? That's right. Zero is always there. Yes. Is it countable? It's uncountable, right? So this is, I mean, although we are removing, a significant chunk each time, we are still leaving a lot of points inside each EK, so that ultimately I'm getting an uncountable set of numbers, right? And there is this a a description to the numbers that are left behind. Are the numbers which if I'm using the base 3 digit expansion, it doesn't contain the digit 1. Yeah. So we ask, uh, actually, yeah, before asking anything here, let's look at some of the basic features of this set. The first one is that it's self-similar in the sense, uh, that is a union of two scaled copies of itself, where the scaling factor is 1 by 3. Yeah. The second one is that it has what we call fine structure. In other words, as I zoom in, like, I mean, yeah, if I go down, further levels, you'll see more and more gaps between these, between the points in E, right? So there is detail, you could say, at all levels, um, yeah, at all levels. At every scale, say. So here, I mean, in this case, um, I can write basically E as uh, well, strictly speaking, I'm going to um, come up with this. I'm going to define two maps here. The first map basically takes x to x by 3. Yeah. The second one takes x to 2 by 3 plus x by 3. Yeah. Then E is basically, so let me call the first map T1, the second map T2. Then E is T1 of E union T2 of E. Yes. I mean, I don't want to be so concrete here because I thought the whole idea was just to give a brief description or an outline of what kind of sets we are looking at here. Right. Yeah. Thirdly, this is these sets are defined in a recursive fashion. Yeah, so it's clear. I mean, this is how we have defined the Cantor set. The fourth would be locally. The local geometry is very complicated. Locally is just a, it's just a set of points with varying gaps in between. And finally, you can see that its length is actually zero. In other words, a set of measure zero. So it's a thin set. In other words, it's a measure zero. So that's my first example. Okay. The second example I'm going to give you is the Von Koch curve. Here, I'm going to construct a fractal set in R2. Okay, again by uh, again through a recursive process. I'm going to consider first E0 as before uh, the unit interval 0, 1, and E1 now is going to be, okay, I should give more space here. I divide this interval into three parts again. And then I construct an equilateral triangle here. Okay. Now offside 1 by 3, and then you remove this portion. So E1, that doesn't exactly look like an equilateral triangle, right? So E1 E1 is a it's a union of four line segments, each of length 1 by 3. Yeah. Now E2, we define again by uh, in the same fashion. So we now divide each line segment in E1 into three parts, and then you form an equilateral triangle using the middle portion. And then you remove that portion in the line segment and replace that with the two other sides of the equilateral triangle. Yeah. So that will give me a set of the form. Forgive my artistic skills. These are all every line segment have the same length. Okay, so keep that in mind. And here, the length of each line segment is in fact uh, is 1 by 3 squared. And if I follow this construction, EK is going to be a union of how many line segments? 4 power k. Yeah. So ek is union of 4 per k line segments, uh, each of length 1 by 3 per k. Yeah. Now, earlier, so over here, what was the reason why we had a set of measure 0? Because if I look at ek over here was union of 2 per k intervals of length 1 by 3 per k, and its length is 2 by 3 whole per k, and as k goes to infinity, this term goes to 0. What is the case here? As k goes to infinity, you can see that the total length, the total polygonal length is actually going to infinity. Yeah. So here you have a set in R2 whose area is 0, but its length is actually infinity. Yeah. Um, yeah. So as you can see, I mean, for larger values of k, the distance between ek plus 1 and ek is shrinking, and then I am taking the limit here. And whatever object, whatever rough object that you obtain at the end is called the Van Gogh curve. Again, you can see that there are certain features that this set shares with that of the middle third Cantor set. Um, Perhaps I don't have to write this down. I think it's visible, obvious here, right? So it's self-similar again. In this case, however, E is going to be a union of 4 different copies of itself. Four different copies of 4 different scale copies of itself, where the scaling factor is 1 by 3, right? So you have that self-similar structure. And secondly, it has fine structure. If I zoom in, you can see more and more irregular sharp edges. Yeah, it it's defined in a recursive fashion. And finally, again, it has a local geometry. Like, I mean, although we call it a curve, it doesn't make sense to even talk about the tangent line, to this limiting object, or to this limiting set. I mean, not necessarily all. In this case, yeah, in this case, you can say they are like similar, but not necessarily all the time, right? Because by recurse, I mean, you're comparing these two, aren't you? Yeah. So by recursive, by this property, I just mean that it's defined in a recursive fashion. Yeah. I mean, I could have defined it like in a recursive fashion without introducing any, like, uh, um, any further, like, additional detailing at each step, right? That's I mean, you're right. I think they are essentially the same. Yeah. Okay. So yeah, so you can see that even in this case, yeah, we talked about the first 4 items, and now I have a set that has, that cannot be properly measured using the two-dimensional measure or the one-dimensional measure, because by two-dimensional measure, it's a measure 0 set, whereas the one-dimensional length is basically infinity. So even that is not telling me how to actually measure the size of this guy. Yeah. So okay, and as I've said before, and as I mean, here you can just take the maximum distance between any points, and as you can see that as increases, the distance is actually shrinking. Yeah, right. So yeah, okay. So that's the, as I was saying, this is the class of um, sets that we would like to consider. And as it turns out, it's not just a mathematical curiosity, for as a well, the reason for considering these sets. It has wide range of applications in various areas. Like if I'm looking at applications within the pure branch of mathematics, you can see that such sets do appear, for example, on questions related to the convergence of Fourier series, or on certain sets related to Diophantine approximation, or the what do you call random processes, or towards the, I mean, towards the applied end, you find these patterns in, for example, the contours of clouds, or maybe in stardust, or very recently, I think, I mean, I was discussing this with some of the faculties today. I happened to attend a talk last week, and over there, it was given by a graduate student who was working in the School of Biological Sciences at ISER Barampur. And she was trying to distinguish between two types of brain tumors. You have got glioma and brain metastasis, and these are they were using the MRI images of these two tumors to identify which one is which, um, and apparently they were using some like a notion called the box counting dimension, um, to actually distinguish between these two patterns. So the area also has, these problems also has life saving applications. Yeah, I mean, I was like quite excited about that. Right. Yes. On each vertical line, how many? Yes. Yes, I'm sorry. When you say you're taking a vertical line, you're just fixing one vertical line. Right. Yeah. So you're asking, for example, if I consider a vertical line here, that's what you're asking? As k goes to infinity. It cannot be finite, right? Because so considering a vertical line is equivalent to like taking a horizontal line as well, right? Because whatever modifications that you're making along this line is equivalent to what you're doing here. And here I can see that as k increases, you're going to have more and more bumps. That's right. Because you're saying because it makes an angle from the. Yes. Yeah, that's right. I mean, yeah, but I think he's asking about this one particularly, like as in. Yeah, I mean, I don't know. I have to think about it. Yeah. Yes. Yeah, I mean, it's actually, one of the major questions people study in this field is the slicing problem, and that's what you're asking essentially, right? You're slicing the curve, this curve, and then you want to see how what is the intersection that you're obtaining in there once you take the slices. Okay, Right. So now I think, you know, I'll be a bit more concrete. And so, okay, let me first give you the goal. Okay. So we are going to try to understand how we can measure the size of these objects. Okay. Or how we can make sense of the dimension of the object. Now, I'm not going to compute the dimension of the Von Koch curve, but the reason why it has zero, two-dimensional area and infinite one-dimensional length is because it has a dimension that lies strictly between one and two. Okay, and in the case of the Cantor set, we will see that its dimension is in fact log two by log three. Okay, so that's strictly smaller than one, which is why you have a measure zero set over here, right? And yeah, okay. So there are various types of the various notions of dimension, and we are going to stick to a notion called the Hausdorff dimension. Okay, and in the case of Hausdorff dimension, you compute the dimension of a set by first trying to figure out what is the right way of measuring the set. So first, I'm going to introduce what is known as a Hausdorff measure, and using Hausdorff measure, we are going to define Hausdorff dimension. Okay, that's the plan. Okay. So suppose F be a family of subsets of Rd, and zeta is a set map. We make two assumptions here, okay? First one is that for each delta, there exists E1, E2 in in F with the with the diameter of each EA at most delta, and zeta of sorry, and X is written as a union of eta i's. In other words, what is X? X is simply RD. So in other words, for any delta, I can cover RD with, these small sets. Small in the sense their diameter is at most delta. Okay. The second assumption is that for each delta, there exists E in curly F such that the diameter is bounded above by delta, and the zeta value of E is also bounded above by delta. Oh, right. Okay. Thank you for pointing that out. Where diameter of E is the Acha, that's enough. Okay. Right. Now for delta and A in RD, we define the psi delta content to be the infimum Yeah, okay. Psi delta of A is the infimum over all the sum of all zeta i's, where A is covered by these EIs, and EIs are coming from the collection curly F. So this value psi delta uh, is actually determined by two parameters, right? Which is say the zeta function and my the collection of sets from which I'm drawing the sets EI. So this definition, so with this definition, you can see that the reason I have introduced or made these two assumptions is that with assumption 2, I can show that psi delta of the empty set is 0. Yeah. And with assumption 1, you can actually uh, show that this infimum, the set over which I'm taking the infimum, is non-empty given for any set A. Okay, so that's why you had to make these two basic assumptions to begin with. So you can check that psi delta is, so as I said, my goal is to, introduce what is known as the Hausdorff measure. Yeah. And this construction, I mean, through this construction, we are trying to, define a more general notion of measure. Not, I mean, we are going to see that the concept of Hausdorff measure comes as a special application or a special case of this construction. Okay. But so you can check that psi delta satisfies certain properties of the measure, of a measure. In particular, it's going to be monotonic. It's going to be sub-additive. Yeah. And as we have just said, I mean, psi delta of empty set is 0. So it's an outer measure. Okay. But unfortunately, it's not, I mean, it's not going to be, or it may not be countably additive. Okay. So, okay, I'll just mention the first two properties here. Psi delta is monotonic. In other words, if A is a subset of B, then psi delta of A is smaller than psi delta of B. Secondly, countably additive. That is psi delta of union of AI is bounded above by sum of psi delta of AI, and psi delta of the empty set is 0. However, as I said before, it doesn't have to be countably additive. So I'm going to leave this exercise here. S is between 0 and 1, and curly F is simply all the subsets of RD, and zeta function be defined as, do we have a question? As diameter of E to the power S, okay? And then you consider the psi delta. So this guy, so the exercise is this, show that this guy is uh, not additive. I'm going to give you a hint. You can just take these two sets. Take U to be the ball of radius delta, and U bar is simply the closure of this guy. So that's an open ball. And then you look at the boundary. And then you verify that psi delta of U is same as psi delta of U bar is same as psi delta of the boundary of U, and they're all equal to delta power S. Okay, so that's an exercise for you. And yeah, so because of this reason, I want to modify psi delta to get an actual measure. Okay, so I'm going to construct the actual measure. We are going to take the limit of of psi delta as S delta go to 0. Um, so we define psi of A as the limit of psi delta of A. And from the definition, it should be clear to you that if delta say is smaller than delta prime, then psi delta of A is actually larger than psi delta prime of A. Yeah. So this is in fact equal to the supremum overall psi delta of A. Yeah. Yes. No, I mean, see, assumption 2 was there just to make sure that psi delta of the empty set is 0. Yes, that's it. No. Yeah. I mean, I just wanted to make sure that psi delta is an outer measure. Yes. All right. So this measure that you have obtained is the guy. So we are going to show that psi is a Borel measure. Okay. Yes. Yes, that's right. Psi delta depends on a delta. Oh, did I? Oh, wait. Oh, I'm so sorry. Thank you for pointing that out. Yes. Thank you. Yes. Yes. Yeah. All right. Okay, so this construction is coming from Kara Theodori, and I think historically, Hostov used this construction to first show that the Cantor set has the Hostov dimension of. I mean, I don't know what he called uh, that dimension. I'm sure he didn't call it Hostov dimension, but he showed that Cantor set has a dimension of log 2 by log 3. Okay, so we are going to look at some of the specific cases of psi deltas. Okay, so firstly, I'm going to choose uh, the zeta function, some specific cases. So let's choose zeta function to be the nth power of the diameter. Okay, well, um, okay, maybe instead of looking at the specific cases, let me first show that or let me convince you that the object that we have attained finally is in fact a measure. Okay, so psi is a Borel measure, and two, if the members of my family curly f are Borel sets, then psi is also going to be Borel regular. In other words, for any set A, you can find a Borel set B containing A such that psi of A is same as psi of B. If my original class of sets are all, I mean, if they are all Borel sets, right? So I'm just going to prove item number 1, and I'm going to leave item number 2 as an exercise. The proof is, in fact, actually quite straightforward. It's you know by using these properties of psi delta, it's easy to check that psi is also monotonic, and it's countably subadditive. Yes, I've made the same mistake here. And I mean, clearly zero when I am measuring the size of the empty set. Okay. Now, to check whether psi is a Borel measure, in other words, to check whether if all the Borel sets are psi measurable, I'm going to use the Kara-Theodori criterion. Okay. The Kara-Theodori criterion. And what does this criterion say? Uh, if you start with, um, we can just write this as a lemma. If on RD, then mu is a Borel measure if and only if mu of A union B is equal to mu of A plus mu of B whenever A and B are um, subsets of RD that are positively distanced apart. Okay. All right. So I'm going to, okay, in view of this criterion, we just have to verify whether this condition holds for our measure psi. Okay. I mean, is it clear to you why this criterion should hold for psi when mu replaced with psi? Let's see. So take verifying the criterion. So we take two sets A and B in RD with the distance between them being strictly greater than 0. And I mean, since psi delta is countably, I mean, since psi is countably um, subadditive, actually, since psi delta is countably subadditive, psi delta of A union B is anyway going to be bounded above by psi delta of A plus psi delta of B, right? So this is always true for all delta. To show the lower bound, I have to actually choose a delta sufficiently small. So let's take delta to be, say, smaller than the distance by, I don't know, maybe 10, maybe 2 is more than enough. Yeah. Um, in this case, okay, so this is my A and that's my B. Now, if I look at a cover of A union B using sets whose diameter is at most delta, right? Then I can split, I mean, suppose I have a minimal cover, okay? Then I can split that into two covers, one that covering purely A and the other covering purely B. Yeah. So if EI is a minimal cover for A union B with the diameter of EI being bounded above by delta for all I, then I can write this, let me give a name for this collection. Let me call it curly Okay, then I can write curly E as a union of two guys, curly EA and curly EB, where EA is the collection of all EIs that intersects A, and EB, a curly EB defined in a similar fashion. So you probably can see where I'm going with this. Um, in the definition of the psi delta measure, I had this zeta sum, right? And since this is it's actually a disjoint union, isn't it? That is why I've chosen delta to be so small. So this guy can be written as two disjoint sums, where here EIs comes from curly EA, and here EIs come from curly EB. So clearly EA is a cover for A and EB is a cover for B. Yeah. So this would imply, actually, yeah. I mean, from the definition, I know that the right hand side is bounded below by psi delta of A plus psi delta of B, right? Because in the definition of psi delta, I was taking the infimum over all these sums. And so that means, I mean, same goes with B. So this guy, so this sum is bounded below by psi delta of B plus psi delta of A plus psi delta of B, as long as delta is smaller than the distance between, I mean, much smaller than the distance between A and B. And now, I mean, it's just a matter of taking the infimum over all such covers, right? So by taking the infimum, psi delta of A union B is bounded below by psi delta of A plus psi delta of B. Yeah. And and this is true for all small values of delta. Is it? Or- Yeah, and by taking the limit as delta goes to 0, you see that, uh, okay, so for small values of delta, this union, I mean, the left-hand side is exactly same as the right-hand side. And by taking the limit, I see that psi of A union B is same as psi of A plus psi of B. Yeah. So by the Carat-Theodori criterion, we have thus, made sure that the psi that we have constructed is in fact a Borel measure. Yeah. Do you have any questions? Should I wait? Okay. Oh, the call got cut. Is that so? Is he coming? Okay. I- okay. That I think I can change that. It should be okay now, right? Yes. No, I just reconnected the USB. Yeah, yeah. It's working now. I think it's working now. I think this was just loose. Yeah. All right. So let's now look at some special cases, right? I'm actually going to just record the definitions here. So psi delta of A was the infimum over the sums zeta of EI with A being covered by union of EIs and diameter of EI is at most delta. All EIs are coming from the collection curly F. And psi was defined to be the limit of psi deltas, which is same as the supremum. Okay, so special cases. The first one is the Hausdorff measure, which is defined by choosing zeta to be the diameter of E to the power S and curly F to be simply the power set of RD. Okay. With the convention uh, that 0 power 0 is 1 and diameter of the empty set to the power S is 0. Right. So the resulting Borel measure that you obtain psi of zeta F is now, I mean, also depends on S, right? So let me also write, I mean, psi, zeta depends on S. So this guy uh, is called the S-dimensional Hausdorff measure, okay? And yeah, and that's the definition over there. The second special case is a measure that you are very familiar with, the Lebesgue measure. So in the case of the Lebesgue measure, I choose the zeta function to be the volume. Okay. So here uh, we set curly f to be the collection of all rectangles in RD. And the zeta function maps a rectangle to its volume. So that's simply the product of BI minus AI. Yeah. So in this case, interestingly, this is pretty easy to see. Um, the Lebesgue measure is the or psi of zeta f uh, is the Lebesgue measure. Measure, and this is it's actually easy to see that um, this guy is, I mean, by definition, it's a supremum over all of these psi deltas. But for any delta, psi delta of A is going to be the same. Okay. So this is equal to psi delta prime of A for any delta prime. So in the case of, I mean, in this special case, you actually don't have to take the limit as delta goes to zero. Okay. For any delta, if I take a cover of a set using these rectangles, then I can basically decompose this cover into smaller rectangles, right? And without actually disturbing the total volume, the sum of the volumes. So in view of that observation, you see that this is I mean, you don't actually have to take the supremum. It's the same as psi delta prime of A for any delta prime. And it's another exercise to verify this fact. Okay, so please do verify this. Now, having defined the Lebesgue measure, we are going to compare the Lebesgue measure with the Hausdorff measure. Okay, and uh, I claim that the Lebesgue measure is same as the Hausdorff measure when S is equal to D. Okay, so whenever D is an integer here, yeah. Um, so I mean, so in other words, the measure that we have introduced over there, can see that I can define Hausdorff measure for any exponent S. It doesn't have to be integer, right? But in this case, of course, this definition does not make sense if I'm not sticking to integer values of D. And the Hausdorff measure, nevertheless, the Hausdorff measure matches with the Lebesgue measure, maybe except for a constant, whenever I am at integer exponents. Yeah. So that's a good sign that we have defined something more general, right, than the Lebesgue measure. Now, the proof of this statement takes a little bit effort. Okay, so I'm just going to give an outline, and I'll let you think about it. So to prove this, you first have to show that HD is absolutely continuous with respect to the Lebesgue measure. Okay, so you start with a set of I mean, Lebesgue measure 0, and then you show that it is also going to have, the d-dimensional Hausdorff measure 0. And once you show that, you can apply Radon-Nikodym theorem and then say that it's going to be some function times the Hausdorff measure, right? And once you have this, you use the fact that both the Lebesgue measure and the Hausdorff measure are translation invariant, okay? And therefore, the function that you have, the derivative you are going to have, is in fact going to be a constant. So that's the outline of the proof, okay? So I want you to think about it. In fact, with more work, you can show that this C uh, is the um, C is the volume of um, the ball, the d-dimensional ball with diameter 1. Okay. It's also should be clear to you that when S is 0, the corresponding zeroth zero dimensional Hausdorff measure is in fact the counting measure. Okay. So when S equal to 0, you have the counting measure. When S equal to D, you have got the Lebesgue measure, except for a constant. I can also look at some other related special cases. For example, I can look at something called the spherical Hausdorff measure, which is similar to the definition similar to the Hausdorff measure, except that the class of sets F is different. Okay. So here again for we take zeta of e to be diameter of e per s, and curly F is going to be the collection of all balls in RD. Okay. The resultant psi measure you obtain here um, again is called, oh, maybe I should use T here. This is called the T-dimensional spherical Hausdorff measure. Thank you. So this is the T-dimensional spherical Hausdorff measure. Can you compare this guy with the Hausdorff measure? Like, I mean, is there any immediate inequalities between ST of A and HT of A? No, I mean, so in the case of Hausdorff measure, the the class of sets were the power set. Yeah. Here I'm looking at only the balls in RD. That's the difference. Exactly. So ST of A is always going to be larger than HT of A. So that's for sure. Can I obtain a lower bound? Like, can I say that HT of A is actually going to be, I don't know, some like, I mean, it's going to be larger than, sorry, it's going to be larger than some multiple of ST of A. Mm, I mean, you can think about, you can think if there is a way to, let's look at the definition, right? So in the definition, you are summing up the s power of the diameters of, these sets, where these sets is they're forming a cover for the original set A. So you want to see whether I can replace this collection of, sets with some other collection of balls, right? You want to basically compare an arbitrary collection of an arbitrary cover involving arbitrary sets with a cover involving balls. Okay, so I mean, yeah, actually, I can show this. This is pretty straightforward. Um, so this is something that we have just noticed. Um, so it is clear that HT of A is bounded above by ST of A. Okay, and what is not clear is that ST of A is bounded above by 2 power T HT of A. Okay, and this is because if I look at uh, a car of A with say, mm, actually I am tempted to put this also as an exercise. We can discuss this tomorrow if you have any questions about this. Why C power T? Oh, you mean that constant? No, 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 no. It's going to be 2 power T. Yes, yes, yes. Yeah. So think about this as well. Okay. Right. So these are some, special cases of, of the measure that we obtained use characteristics construction. Now I need to record, so I'm running out of time, so I'll just record some of the basic properties of the Hausdorff measure. Okay, properties that we uh, expect. First one is that it's translation variant. And secondly, it has this nice interaction with scaling. So Hs of T times A is same as T power S times Hs of A. Okay, where Ta is the collection of all Tx, where x comes from. Okay, and third observation is that if phi is a Lipschitz map, that is phi of x minus phi of y is bounded above by c times mod of x minus y for all x and y, then um, then hs of phi of a is bounded above by c power s hs of a. Okay, this should come like immediately from the definition. Okay, so you just use the definition, use the covering, and use the right covering and prove this. So these are okay. So you see that as a consequence of the third observation, right? If I have a bi-Lipschitz map, yeah, then the S-dimensional host of measure is preserved. Yeah, I mean preserved up to constants. I mean you have both an upper bound and a lower bound. Okay, so consequently, um, I mean actually I'll mention that anyway during the when we're talking about host dimensions. Um, few other properties, and this is it's a collection of statements. I'm going to write it as a theorem here. So let if curly f is the collection of open sets in RD, or if curly f is the collection of all closed sets in RD, or if it's the collection of all convex sets in RD. So in all these cases, then the psi function you obtain, right, uh, is where the zeta function as in the case of the host of measure. So it's the diameter to the power s. But now I am drawing the sets from these three different collections. In all these cases, this guy is same as the S-dimensional host of measure. Okay. So in the definition of the S-dimensional host of measure, it's not necessary that I have to consider all sets, all subsets of RD. You can just restrict your attention to just the open sets, or in the case just the collection of closed sets, or the collection of convex sets. Okay, so I mean in all three cases you get back the S-dimensional host of measure. However, if I am restricting my attention to the collection of all balls, then you see that the value of the measure can actually change. Yeah. Yes. Yes. I think I'm going to wrap it up like in 2-3 minutes. So the proof of this statement, at least for the proof of B and C, the cases B and C should be quite straightforward. This is proved using the fact that that the convex hull um, or the closure of a set E they have the same diameter. The diameter remains unchanged if you are considering the convex hull or taking the closure. Okay, and this one, on the other hand, is proved by showing that if I start with the cover for the set E, I can actually slightly, modify the cover so that you have now a cover of open sets where the size sum is only modified by a small amount. Okay, so you have to use that fact to show that to prove item number A, item A. Okay. I think I'll stop here. I think we will start the next lecture by defining host of dimension. I think this is a good place to stop. Yes.
Thanks for the talk. So this construction of this psi measure, it feels like it should go through in a lot more general spaces. Uh,
Yes, that's right. I mean, if it's a metric space, for example, I can carry these constructions. Absolutely, that's right.
how about just like first countable Hausdorff or something?
I don't know. Actually,
Okay.
don't know. Um,
Because it sort of feels like you just want the character theoretic criterion to hold, and you need it to be Hausdorff to separate the sets, and then
yeah, yeah. I mean, these things have been generalized to other spaces as well, in these constructions particularly. I mean, I'm not, so familiar with it. So, but I can actually, point you towards certain references. Yes.
and if I can also ask a very philosophical question, it sort of seems like this construction, what it's saying is that if I want to assign a size to something,
Yes.
it is exactly enough to assign size to very small sets, and then everything works out by the
It's
splitting.
exactly sufficient to what is it that you're
Assign
saying?
size to very small,
Yeah, that
whatever
cover
small.
the that
Yeah.
cover the set. Yes, that's the idea.
So
Yeah,
I followed
yeah,
because somehow it just seems magical that it splits like that,
yeah,
and it's enough to just do it for very small sets with no other. Yes, thank you.
yeah. I mean, like to capture its geometry, you have to consider smaller and smaller sets, right? So it's natural in that way. Yeah. But as I said, in some special cases, even like for example, the case of Lebesgue measure, you could see that, I could get the same measure even by just considering large class of, I mean, covers formed by large rectangles.
Yeah,
Yeah. No, actually, that's not true. I'm taking the infimum anyway overall.
overall delta x.
Yeah. So it's still, yeah. But over there, it's not so clear whether the infimum is coming from, covers that are like finer of finer and finer scale. I'm just taking the
Okay,
infimum. It can be,
right. It
yeah,
could
yeah.
point.
Okay. Any other questions? Yeah. Hmm. Hmm.
If you take a sequence of odd integers n1, n2, n3,
Right.
cut the interval 0 to 1 into n1 parts,
Yeah.
take alternative ones.
Yeah.
Each of them you cut into n2 parts,
Right.
take alternative ones,
Right.
keep on doing it. Finally, you get a Cantor set.
Right.
Topologically, this is homeomorphic to the Cantor set.
Right. Right.
But
Right.
did people calculate the
The host
Hausdorff
of dimension.
dimension?
Yeah,
Or
I'm sure. So at every scale, so at every level, you are dividing the
Ni?
interval into
Uh,
nk many
Right,
sub-intervals,
right,
and you're choosing nk by 2 out of them,
correct. Yeah,
right?
right.
All right, yeah.
There should be some formula, right?
Yes, yes. I mean, uh, so each, wait, what is going to be the scale in that case?
But Ni's may go to infinity. You see?
Yes, I got that. I got that. feel like I should be able to say this. So, I mean, in the case of Cantor set, the two comes from the fact that you're choosing, yeah, two. I mean, no, so it's basically log 2 by minus of log 1 by 3, right? So 2 is the number of intervals that are being chosen at every scale, and 1 by 3 is the scale, the scale difference between the intervals in one level with the intervals in the other level.
Right.
So I think, you seem that we should be able to compute the
Right.
Hausdorff dimension of
40,
this guy as well. Yes, yes, yes. Yeah. So since you've mentioned about, uh, this property in topology, like here, the maps that preserve a Hausdorff dimension are bi-Lipschitz maps. Instead of homeomorphisms, these are bi-Lipschitz maps. I'm sorry? I mean, but as I said, like
Yeah.
it's a set of interest. Like there is no definition for a fractal. Yes.
Okay.
Yeah.
See, I was just wondering whether there's any special significance if you selected NIs to be prime numbers,
Yeah.
whether
Oh,
that set has any special significance.
in I mean, as far as computing the Hausdorff dimension is concerned, I'm going to just say that might not be. I mean, it might not have any significance, but
Ah,
at least
I
I've not seen any such constructions. Where
Okay.
the explicit NKs are taken from the collection of all primes. Um,
Mm.
no.
Mm.
There are no more questions. Thanks.